Hey math kids, today we're going to talk about the principles of mathematical induction. And essentially the idea of it is that we test the first case and then from there we test that the next case could be true, but we do it in a symbolic way. And that way, if we know 1 is true, then we know 2 is true. But since we know 2 is true, we also know 3 is true. And since we know 3 is true, 4 is true. And so it just kind of recursively goes through the pattern, and we prove it like that. Okay, so we need to prove that 4 to the n plus 2 is divisible by 3 for all integers and n is greater than or equal to 0 by using the binomial expansion. So first we need to do it with the binomial expansion, and then we need to use induction, mathematical induction. Okay, so what we're going to do is if we plug in n equals 0, so this is for the binomial case, we're going to get 4 to the 0 plus 2, which equals 1 plus 2, which is 3. And so we know that that is divisible by 3. Obviously. Now, if we look at 4n plus 2, which is equal to 1 plus 3 to the n plus 2, because this is really just 4 to the n. So we got 4 to the n, 4 to the n. Okay. If we use the binomial theorem, which I'm not going to go through in detail again, you can watch the video on that one. But we're going to get 1 to the n plus n1, 3 plus n2, 3 squared plus n3, 3 cubed plus n minus 1 plus n 3 to the n plus 2. Okay, that last one is just this. So all of this is the expansion of this, and then we have the plus 2 down there. Now, if we combine this and this, so 1 to the n is just 1, and so 1 plus 2 gives us a 3, and so everything else is multiplied by a 3 or a power of 3, and so everything is divisible by 3. So in other words, we could take out a 3, and that 3 would become a 1. Took out a 3, and since there's a 3 on the outside, we know all of that is divisible by 3. Therefore, this thing is divisible by 3. Alright, now we're going to approach this with mathematical induction. Okay, So when we're setting up mathematical induction, we're going to say P of n is 4 to the n plus 2 is divisible by 3. Okay, so if n equals 0, this is like the first case, then 4 to the 0 plus 2 equals 1 plus 2, which equals 3, which we know is divisible by 3, so P naught is true. So you have to do that, prove the first case, which is P naught. Okay, 2. Now if we assume that PK is true, then 4 to the k plus 2 has to equal 3 times some value a, where a is an integer and a is greater than or equal to 1, like that. And now from here, what we're going to do, we're just going to look at 4 to the k plus 1, which is like our next case. So k, and then we want to look at k plus 1. We assume that case k is true, and then we're proving that if case k is true, k plus 1 is also going to be true. Okay, and then, so I just plugged in a k plus 1. And so we get 4k, 4 to the 1, plus 2. And what we are going to do after that, we have 4 times 4 to the k plus 2. And so 4 to the k plus 2, we can take this and we're going to solve it for 4k. So I'm going to just subtract 2 from both sides. And so 4 to the k is equal to 3a. So I'm replacing this 4k with 3a minus 2. Okay. And then we distribute. So we get 12a minus 8 plus 2, 12a minus 6. And from here, we can factor out a 3, which is 4a minus 2. Okay, and since there's a 3 out here, we know that 4k plus 1 plus 2 is divisible by 3. And since we could start at p naught, which remember that was 3, that's divisible by 3. If we made our k a 0, then we know that p of 1 will also be divisible by 3. And since we know that p1 is divisible by 3, we can make our k a 1, and that would mean p2 is divisible by 3, and it would go forever through everything. And so we know that for all values n, this is divisible by 3.